Hello, welcome to your second video on applied derivatives. This one is about on the topic of optimization. Alright, what is optimization? Take a look at this graph here. This graph represents average cost. Maybe for some business or company, the cost of production based on their output. So as you can see, as there's more output, their costs start high, then their costs go low, they reach this bottom point, and then their costs go up again. Okay, so what is optimization? Well, that point right there would be the optimal place to be for this company. They want to produce things and they want to have lowest cost. So this is like an optimal point. That's what optimization is all about, finding those points. So we can see here the optimal output is right here because it leads to the lowest minimum cost. Okay, the lowest average cost. All right. So here's another example of an optimization problem. We have the sum of one positive number and twice a second positive number, which is 200. And it says find the two numbers so their product is a maximum. So basically what optimization always talks about is either a maximum or a minimum. We just saw the idea of a minimum cost. Now we're talking about a maximum. So let's see what the definition online is of optimization. The action of making the best or most effective use of a situation or resource. Okay, best use and most efficient. All right. In mathematical terms, we're often looking for a maximum or a minimum point because that represents either the best in terms of the best highest output or something, or lowest cost, for example. So max or min is what we're looking for. So let's try it with this simple number problem. So the sum of one positive number and twice a second positive number is 200. How can you write that? I wrote it like this. Okay, so sum means addition, so one number and twice another number, and the sum is 200. So there's one equation. I'm going to rewrite this equation solving for a. Okay, solving for a, we have a equals 200 minus 2b. And I'm doing that because I'm anticipating the next step, because this is often what happens in optimization problems. We have to create a second equation and maybe make a substitution. So what's our second equation? Well, it says find the two numbers so that their product is maximized, is a maximum. Product means multiplication. So write that next equation. Okay, I'm writing as p equals a times b. Their product is first number times the second number. Okay, now we have an equation with two variables. This one also has two variables. So why don't we make a substitution? And in optimization problems, you have to look at which equation are you trying to optimize. Well, we're trying to optimize the product one because we're trying to find the product as a maximum. So we're going to work with this one further. So we're going to take the other equation, plug it into, or substitute into here. So replace a with that, multiply through, and you end up with this quadratic. So the product is this quadratic here. In terms of b, now there's only one variable. The a variable is gone. So now we can move further. When we're talking about optimization, again, we're saying we're often looking for the maximum and minimum points. And we know maximum and minimum points on curves that are graphed are the points where there is no slope, where the tangent line is horizontal. There's no slope. So how do you find somewhere where there's no slope? Okay, you take the derivative. So here's the derivative of that. And you set the derivative equal to 0 because you're saying derivative, which is slope. Slope is 0. When is the slope 0 on this one here? Solve that. Okay, we get a value of 50. Now 50 is either a max or a min point. We're going to double check. Which one is it? And we're going to do that by checking on either side of 50 and seeing what the derivative gives us. So this is called the first derivative test. Okay, so let's apply the first derivative test. What we do is we can create a number line. We can put the value we found 50, because we know at 50 there's no slope. So we're going to check what is the slope before 50 and what is the slope after 50. So what's a number before 50 that we can use? Take any number you want before 50, put it into the derivative, and see, do you get a positive or negative result? Let's try. Okay, I took a number far from 50, but it's definitely below 50. I took a number of 0. I put 0 into the derivative, and that gave me a positive answer. I could have taken any number less than 50. I could have taken 49 or 48 or 47. They would all produce a positive number. What that means is that the graph has a positive slope. It's rising before 50. Okay, let's check after 50. What's happening? Okay, I took a number very close to 50, 51. And when I put that in the derivative, I got a negative value. That tells us the slope is negative after 50. So what that tells you is the graph is going up and then down. And we already know 50 was either a max or min, and if the graph is going up and down, then 50 must be a maximum point and we have solved the problem. Therefore, b equals 50 is a maximum. We have found out a maximum point that produces maximum product, okay, maximum product. And therefore a is 100, because I took the b value and put it back in here and I got a. So I have found out the 2 points that produce a product that is a maximum. All right, let's look at another common optimization problem. Here we have an open box. It has a square base and an open top, and its volume is given to us. It says find the dimensions of the box that minimize the surface area. So the thing we want to optimize is the surface area. But this time we don't want to maximize it, we want to minimize it. Because that makes sense. In the context of a company maybe producing things like this, they want to minimize the amount of material. They want to have a certain volume, but they want to minimize the material used. So that's what we're going to do here. We're going to optimize it like that. First of all, it tells us it's a square. So what does that tell you about the base? Well, I'm going to call this side B, but this side will be B also because it's a square. I'm going to label this height using H. Okay, can you make an equation for the volume? Okay, so volume is length times width times height, so B times H, which is B squared H. And we know the volume is 32,000, so I can replace that V with that. So there's that equation. And again, as with most optimization problems, I have an equation with multiple variables, so I can't really solve that. But I can maybe make a second equation that's going to work. But again, this is not the equation we want to optimize. We don't want to optimize volume. We want to optimize surface area. So we need another equation for surface area. So we know that we're going to take this maybe and substitute it into the surface area one. So how about solving this for a variable? Which is easier to solve for, B or H? Well, certainly H is, because we can just divide by B squared here. So now I have this from this equation. Let's make one for surface area now. What would be your equation for surface area of this? Okay, here's what I have. Surface area is 4HB. Why HB? Okay, H times B is one of these sides. And then this one is also H times B because it's a square. So I have 4 of those sides that are HB, 4HB, plus B squared, which is the bottom, B squared. Okay, there's the whole surface. Now again, it has 2 variables. But in this previous equation, the volume one, I found H. That means I can substitute for here. Okay, so my area formula then with that substitution made is this. This can be simplified, of course, so simplify it. What do you get? I got this. Okay, the 4 times 32,000 is this. That b squared I moved up, made it b to the -2, and when you multiply by that, you combine those to get -1, and there's that. Okay, there's our area model. We want to minimize the surface area, so we have to find the derivative and then find that max or min point. Okay, so here's our derivative. Check your work carefully on that. And now we're going to set the derivative equal to 0 because we want to find out when does this derivative, sorry, when does the original function have no slope. And that's what we're going to solve here. So solve this. What do you get? Oh, what did I do here? Not only did I make that 0, I also changed this. What step did I do here? I multiplied everything by b squared because multiplying this by b squared will cancel away those b to the -2 and b squared will cancel each other. And then here, that times b squared is this. Okay, this can be solved. Solve for b. Okay, b cubed equals that, and that means b equals 40. So we just found out 40 is either a max or min point for the area function. And let's confirm again. Let's check values on either side of that. So here's 40. Okay, check a value less than 40 in your derivative. I used 1. And when I put 1 in there, I get a negative value. So that tells us the area function's decreasing before 40. And then take a value greater than 40. I took 41, I get positive. So that means it's positive after. So it's decreasing and then increasing. So that tells you for sure 40 is a minimum point for the area model. And that's what we found, a minimum surface area. Great. And then H must be 20. I can get that from here by putting 40 in here for B. All right, we found 2 values that minimize the surface area because we found a minimum point. Okay, let's try another one. Here's a function that represents some kind of costs. Your job is to minimize, find out how many items X, the X value that will minimize the cost. Try it out. And let's try it out. Let's see how it goes. Okay, now check your work. Here's the derivative. Set the derivative equal to 0. solve, and you get two answers for x, but we only use the x equals 3 because -1, we cannot produce -1 items, so we're going to use only the positive one here. Okay, by the first derivative test, right, you put 3 on there, you check a value below and a value above in the derivative, you get negative and positive. That means it's decreasing and increasing. So if it's going down, the cost model is going down and then up, then this must be a minimum point. So we have found somewhere to minimize the cost. Great. Let's try also with the second derivative test. Let me remind you what the second derivative test looks like. And here that shows what's going on here, down and then up. Okay, second derivative test. Okay, sorry, I'm jumping ahead of myself. So therefore x equals 3 must be a minimum because the slope is negative and then positive. Okay, so second derivative test. Let's remind ourselves what that is. That's another way of checking if a point is a max or min. But we check it with the first derivative, we check derivative values on either side of that potential max or min. With the second derivative test, we don't test on either side, we test the actual point in question. So what we do is we find the second derivative. So this one here, second derivative is this. And now into the second derivative, we put that point, that one that we know is either a max or min. So here we're going to put 3 in there. And when we put 3 in here, we get a positive value. And remember, second derivative tells us about concavity. And when we get a second derivative value that's positive, it tells us the graph is concave up, just like what we see here. And if a graph is concave up, and we just put in a point that we know is either a max or min, well, that point must be a min, because if a graph is concave up, there's a min point right there. If it gave us a negative answer, then it means the graph is concave down, so the other way. And that would tell you the point must be a max. Some students find second derivative test easier to use than first because you just put the value right in the second derivative. All you have to do is take first derivative, second, put the value right in there. Might be easier than doing all this. All right, good. So therefore, this tells us it's concave up, and therefore x3 equals 3 is a minimum. Two ways to check. Okay. Hey, look at this problem. This might look familiar. This is one of my favorite kinds of problems. We've seen ones like this last year in our course for sure. Read this carefully. It tells you about a rectangle. It tells you about a curve here that's represented by this function. And it says the coordinates of point B are x0, so I'm going to label that here. This distance is x, and this is 0 on the y-axis. And then point C here has this coordinate. Okay, it has the same x values here, so x, there's x. And then the location of the y-coordinate here, well, it's on this curve. So there's a y value, right? Y equals that. That function represents the y value everywhere. So that's your function that tells you the location of this point. All right, write an expression for the length of AB and BC in terms of x. And then write an expression for the area of the rectangle as well. Well, let's do A first. Okay, let's check your work. AB must be 2x. If this distance was x, then this is 2x. How about BC? BC must be, what was BC asking for? Oh yeah, this length here. And that length here is the y value, right? So the y value right there. And then the area is just base times height. So we just did 2x times the base times the height. 2x times the height, we found the area. Okay, now we know an equation for the area here. Our next goal in this question is find a primed of x. So find the derivative of that. Okay, check your work. There's the original function, there's the derivative. Whoa, all right, we're using product rule and we're using derivatives of cosine, and there's a chain rule there. There's so much to look at there. That was our last lesson. Take a close look, make sure you have the proper derivative. Pause if you need there. Okay, now that we have the derivative, it says use your answer from that last one and find when the area is a maximum. We're going to maximize the area. So we want to optimize the area model that we just created. Okay, here's an issue. Here's the area model we had. We set it equal to 0 to optimize it, right, in order to find out when there's no slope. However, this is very hard to solve algebraically, so don't worry about doing that. We're going to do this by graphing in your calculator. So graph this function on your calculator and find out on your graph when that function is equal to 0. Okay, let's check. So here's the graph of A primed, and it's equal to 0 right here. Find that point. And on your calculator, we know how to find that. It's x equals 1.72. That tells us when this length is 1.72, we have the optimal area here, maximized area. Okay, let's check this another way. Verify it by graphing the original a to the x, the ax function. Okay, here it is. Graphing ax function looks like that. Now where is the maximum point? Ah, the maximum area is here. So that point should match this one. and it does. Really important connection. Take a close look, and great job.